and I'll keep muted because it's quite noisy out here. So good afternoon to John, Ian, Mike, Peter, Stephen, and Caleb. Thank you very much for joining us. Evidently, none of you have Rogers, and you're able to connect today. So I'm going to turn over the meeting to Caleb since I really don't have access to my full computing power at the moment. And we're very thankful that Caleb has agreed to help us with our programming in our mentor sessions. And it was a really great session last night, and this will be the second of our 2 sessions. So thank you again, Caleb, and I'll turn it over to you.
All right, thank you so much. Yeah, so just kind of following up from yesterday, we kind of went over the basic way to program a robot just using a single file in WPI-lib using Java. And then we kind of went over how Symbotics 11.14, how we like to program our robots. And then today, basically, what we're going to do is basically pretend that it's the start of build season and kind of go through how we would program a robot. And I'm just going to pick like an old robot of ours as an example. And we're going to kind of start off with just sort of our blank template and just kind of fill in what we would need to actually use this, program this robot. Yeah, so just for an example, we're going to use our old 2018 robot. This robot had a tank drive, had an elevator that could go up and down, and had an intake. So overall, it didn't have too much going on in terms of programming. So I thought it would be a good idea to use that as an example. Yeah, and basically we're just going to get started. So I pretty much went ahead and cleared out everything. And so this robot is basically a blank robot. It has no motors, doesn't have any sensors. The only thing is it just has all the camera stuff just in case, but actually for this robot, we didn't even use a camera. So that stuff could get deleted as well. And this is pretty much what we would be starting with at the start of the year. So our constants, oh, this still has a bunch of swerve drive stuff, which we won't need. So we can just go ahead and get rid of all that. Yeah, and then basically what we'll need to do is start adding things in as we need them. So right now, like our teleop control, for example, doesn't have anything going on in it. It actually just has some drive-based stuff, which is from a swerve, so we also don't need that. And it also in here. Okay. So the first thing we're going to do is start adding in our motors. Just get rid of this limelight stuff. Yeah, so right here, we're going to start adding in our motors. So this robot had a tank drive with actually it's 3 motors on each side, but it doesn't really matter if it has 3 or 4. So we're just going to do it with 4 because that's what most robots have. And that robot, what it did is it had a Talon on each side and with an encoder in each one. But I know like not everyone has Talons and stuff like that. So we're just going to program it with more basic speed controllers for now. So we're just going to do like Sparks. So we made the objects for the speed controllers. And just like for the basic code that we went over, we're just going to put in what port each motor's in. We also had motors for the lifting mechanism, the elevator that could go up and down, and motors for the intake that could pick up the cubes that year. So we're just going to make all the motors now. So we got the drive motors. We have the elevator. We're going to have the intake. Now some of these, like in real life, had like more motors than just this, but all the motors just did the same thing. So the code is going to be identical. Did capital. All right, so we made all the motors. Now we can start adding in functions to basically set the motors. So we can pretty much just go down here. Just make a public void, and then we can do like set drive. And then we could label this like forward and backwards and then turning, or we could do X and Y. We can just do forward. Because it's a tank drive, we need the right side to be going backwards when we're turning. The same thing with the elevator. So now we have a function we can do to set all the motors. We're just going to do this little this stop function. We're just going to fill this out, turn everything off by setting everything to 0. Okay, and then now we have the motor set up. We're ready to basically, we can just start adding in our controls. So we're going to go over to driver input. We already have some controls just for getting the analog sticks from the driver. So we'll use that for driving and turning. We'll just add some for the elevator. So we'll do a, for manual control, you could use the right stick. So we actually have the right Y stick here, just to manually move the elevator up and down when you're testing. So we already have that, but we'll need to add something for the intake. So we'll do intake on. And we'll just do the green button on the controller. and we'll do the red button for turning the intake off. And we can actually rename this to being get elevator manual. That way we know that it's manual control for the elevator. So we've added the buttons now. Now we could just go into our drive. And basically here's where we're going to want to actually have it talk to the IO class and actually set the motors. Just go ahead and get rid of all these for now. So since we need to talk to the IO, we're going to create one here, import it. Now we can access it inside of the drive class. And then basically all we need to do is need a function for setting the drive. And then we can just kind of have it make a variable to keep track of the forward and turn. And then inside of set drive, we can just make forward. So the this dot is basically saying we're referring to this variable. And then just having turn means we're referring to the variable inside the parameters here. So that's why we have to add this dot to specify that we're talking about the one created up here, not the one inside here. So now that we have a function for basically getting the values for, that we want to be going, all we have to do now is inside calculate when we're in output control, which we're always going to be in output control by default right now. Yeah, we're already in output control. So basically all we have to do is when we're in output control, we set the motors to be going that speed. Then when we're disabled, set it off. So now we have the drive able to basically get how fast it wants to go being set somewhere. And then during calculate, it's going to actually turn the motors that fast. Now all we need to do is actually have something called this function to actually be setting the motors. And so we're just going to go into our Untitled Controller. This is where we pretty much are going to access all of our subsystems. Just getting all these unused stuff. So in here, basically what we can do, we already created a drive. So all we have to do is inside our calculate, this is where we're going to get in our speeds from the controller. So what we can do is either we can make a variable over down here called double X. And just like when we had the single robot, we're basically just going to be getting our X and Y values from the controller and then setting them to the drive. So right here, we're going to be doing so now every loop, we're going to be getting our X and Y values from the controller. And then all we have to do is now set our drive to be going the X and Y values. So we can go this dot drive, set drive. So our forward is going to be our Y and our turning is our X. And that's basically how we added tank drive controls for the robot. So now, basically, if we go to the robot.java in teleop periodic, which happens every loop, it's going to be running teleop control.run cycle. If we follow that in, that's going to be running teleop controller dot calculate. And if we go to teleop controller dot calculate, that's this function, and that's what's going to be setting the drive. And this is what actually sets the motors if we follow it all the way through. And so basically what we can do is we can do the same thing just now for the elevator. So what we'll need to do is make a new subsystem. So right here we have the drive. We're going to need another one. So we could just copy and paste this. Just Control V, I guess. We'll rename this one to elevator. And then we can just kind of rename everything that's drive related to elevator. So we're going to elevator state. We won't need this. What's wrong with that? Oh, instance is drive. Yeah, I probably could have just like renamed everything called drive to elevator, but did it the hard way, I guess. So now we have the elevator subsystem created. Now what we'll need to do is just basically add a way to set the output manually. It's going to be just like how we have a function for setting the drive. So we can just make one right here. Then we can just create a variable for keeping track of the manual control. And then when we're in output mode, which is going to be our manual control, we just need to make the motor whatever this value is. So just like in the drive where we were basically taking in whatever our forward and turn values were saved as and setting it to the IO to set the drive, we're doing the same thing with the elevator. Whatever our manual output variable is set to, that's what we're going to tell the motor to go. So the only other thing we'll need to do is basically just like how we did with the drive, we need to add something in teleop controller that's basically taking in our control input and then telling the elevator to go that fast. Now, since we just created a new subsystem, we're going to have to add it up here. And it's going to be confused because it doesn't know what it is. So we got to import it. Okay, and then now we just need something to basically get our right analog stick. So we can just do double. And we're going to make that equal to elevator manual because that's what we named it in driver input. And then we can just do this dot elevator dot set elevator manual. And then all we need to do is make sure that the calculate is running for this new subsystem that we added. So every cycle, this calculate is going to happen. And then when that happens, it'll check what mode it's in. Right now, we only have output mode, so it's always going to be running manual output mode. And then we're going to be setting the motor to go whatever this variable is set, which is what we're doing here. We're setting that variable every cycle. Now, eventually, what we're going to do is have some sort of toggle where we're only in manual mode after you press a button. And then otherwise, we're going to be using like a PID control. But for now, we just have the manual control. And so now we have the drive in the elevator. Now we just need to make the intake. So we're just going to follow the same process pretty much. Make the intake. I can just like find and replace. Seem to have worked. Yeah, so basically we have everything that we have for the elevator. We have a way to set the manual output. We have just an output state. Now, actually for an intake, it's not going to work like the elevator where we either have presets or manual control. For the intake, we're pretty much just going to have 3 states. We're going to have an intaking state, an outtaking state, when we're spitting balls out, and then a off state. So instead of doing output, we're going to make intaking, outtaking, off. Won't need that. So won't really need this. First cycle, we'll set it to be off because when the robot turns on, we want it to its default to be on off. Then what we can do actually is just add since we don't have output anymore, we can just get rid of this. And what's nice about these switch statements is that you can click here and say, oh, usually there's an option to generate. Oh yeah, here we go. Add missing case statements. So it'll kind of auto populate the 3 states that we made. And then we just need to add the code of what to do when we're intaking. So when we're intaking, we're going to set the intake to be going a positive number, like 0.7, let's say. When we're off, turn it off. And then when we're outtaking, we're going to go negative. What if the elevator has that error too? Yeah, it does. Okay, so now we have the 3 possible states for the intake, where they're intaking, turning it off, or outtaking. Now all we have to do is basically check, make something set those states. So if we go to teleop control, the same thing, we're going to add our new subsystem. import it. Okay, and then now all we have to do is need to run the calculate for it. And then we need something that's going to set the intake state. So what we could do is we can say if this dot driver input dot get intake on button, then we're going to set our state to be the on state. So this dot intake dot set state, intake state dot intaking. Now I just realized that we don't have a button for actually outtaking, so we're going to go back and add that. So we just go back to our driver input. We have the intake on, intake off. Just make a new one called intake reverse. Make that the blue button. And then we can go back to teleop controller and keep filling out the else if. So if we're pressing the reverse button, we want to set the state to be outtaking. And then if we're pressing the off button, so basically now we have an on, a reverse, and an off. What we could also do is have it so if we're not pressing on or reverse, it will just automatically put it off. That's what we usually do. We have one button for in, one button for out, and then if you're not pressing anything, it just shuts off the intake. So to do that, all we would have to do is get rid of this else if and just make it an else. So basically, if we're not pressing either of these two, it's going to go off. And we can just add the disable part. In the first cycles. Right now, they don't do anything because they're blank, but eventually having these might be needed. Yeah, so now we have the drive base, the elevator, and the intake running on manual control. So from this point, basically, we would start trying to automate stuff. So the intake, it's fine, just leaving it with an in and an out and an off. You don't need any kind of sensors for that. Same with the drive, it's pretty much fine how it is, just using the sticks to turn and go forward and backward. The only thing we're going to need to kind of add sensors and kind of automate is the elevator lifting up and down. So we're going to go over how to do that. So this game basically had 3 different heights, essentially. It had on the ground, when you're just driving around, you would lift up to place cubes into this, which is called the switch. And then also there's the scale. So you would lift up all the way up to the scale. So we're going to want 3 different heights that we can go to. And we don't want our drivers having to manually try and get it to the right height. We just kind of want it so you press one button and it automatically lifts to the exact height. So we're going to make a PID controller to handle that. So the first thing we're going to want to do is add in the encoder. So we're going to go back to our IO. And just like what we did with adding motors, we're going to do the same thing. Except this time it's going to be an encoder. Now we have our own util classes that we've made for encoders. Same with we've made our own PID and stuff like that. But our encoder is actually just a it uses the built-in WPI-lib encoder. It just kind of adds some extra stuff to it that we used to need to have. We don't really use these types of encoders anymore. Now we just use the built-in encoders. So if you have like a Neo or a Falcon, or if you have like a Talon with the Meg encoder connected to it, you would just use the Talon's built-in PID. But we're just going to assume that we don't have that. So we're going to make a new elevator encoder here. Now these encoders are going to be plugged in. They actually have two different, it's 4 wires, and basically 2 of them go into one slot on the RoboRio on the digital input, and then 2 of them go into another slot. So the A and the B channel are what slots they're going into. A trick you can do is if you find that the encoder is going backwards, all you can do is just replace which one is A and which one is B, and that will actually invert the encoder. You can also, on the RoboRio, just switch the wires around as well to invert it. Or you can just add like a negative sign in the code. So there's like a bunch of ways you can invert an encoder if it's going the wrong way. Yeah, so now we've made our encoder. Now basically all we need to do is make a thing that can kind of read the value from the encoder. So we're just going to make a new function down here called like get elevator encoder. And that's just going to return the amount of ticks the encoder has gone. Now what we could also do is if we knew the gearbox and the ratio and how many ticks per rotation are on our encoder, we could do something like get elevator height. And then what we could do is basically just take the encoder value and do some math basically to convert it from encoder units to whatever unit we want to use, whether it's like inches or feet or meters or something like that. Usually we use feet just because the game manual is in feet. So it's a bit easier just to kind of say, okay, this thing is going to be, the manual says it's going to be like 7 feet tall. So you can just convert things to feet, and then that way you can have a button that just lifts it up straight to 7 feet. But I don't remember offhand what our ratio was or anything like that, so I'm just gonna leave that part blank. We're also gonna need a way to kind of reset the encoder at the start of the match, just reset it to 0 when it's sitting on the floor. So we can just kind of do that down here. And we're just gonna go reset. So now we have an encoder. We can get its values. Now basically all we need to do is make a PID controller that can take in the encoder and then lift the elevator to certain heights. So what we're going to do now is make a PID. So if we just go over to our elevator, we can go up here and we're going to use the WPI-lib PID. So I believe it's just PID controller. So this is built into WPI-lib. Even if you're not using our Symbotics code, like our Symbotics PID, you can just use the built-in WPI-lib one instead. They're pretty much identical. And we're going to call this elevator PID. Now what we need to do is basically set it up so it has the right constants. So we can do that in a couple places, but we'll just do it in our first cycle. Now this is basically where you would type in your PID values. PI and D. Now we don't know what those are going to be yet because we haven't tuned it. So we're just going to go set those to 0 for now. One thing you can do is make these smart dashboard values. That way you can tune your PID on the smart dashboard and you don't have to download code every time when you're changing these PID values. We have our own dashboard thing where we can push stuff to the dashboard from robot constants here. So we'll get into using that after, but for now we can just hard code in the numbers for the PID. So now we've made a PID controller. Now what we need to do is make the states for the elevator. So right now we have that manual control, but we want to add in different heights that we can lift to as preset buttons. So what we can do is first, we can just add the states here. So we want to keep the output just in case we ever need to go in manual control in case the encoder breaks. But now we can add in our heights that we want to go to. So this would just be like a label for them, not the actual value that we want to go to. So just gonna call it the floor. We're going to call it the switch for the switch height. And then we're going to call scale. So those are the 3 different heights we can go to that we want to go to while we're playing the game. So now that we added those, we're going to basically create more cases that we can go through. So we now have the floor state. And then we also have the switch state and then the scale state. So now what we'll want to do is we could either make, we could have values up here, basically recording all the different heights that we want to go to. Like I said, we usually use feet, but right now we haven't converted to feet. So we could just use the encoder ticks that we want to lift to. What we like to do though is have this file called robot constants, and basically anything that's like a constant, we want to record it down here. So what we can do is just make a new section for elevator constants. And then we're going to make a new it's going to be a public static double. And we're going to call it floor height. Which is going to be 0. And then we're basically going to make a new one for the switch and the scale. Again, these could just be constants like inside of the elevator itself, but we like to keep things more organized and have all the constants in one place. And then we can just kind of guesstimate and say, okay, the switch is 2 feet tall and the scale is like 7 feet tall. And these can be decimals. So now in our actual elevator itself, all we have to do is basically tell the PID to go to that target. So we're going to say this dot elevator PID dot calculate, and basically we just give it where we are currently and where we want to be. So where we are currently, that's going to be from our sensor. So we're going to say this .io.get elevator encoder. And that's basically just going to give us back where our position is from the encoder. And then our set point is going to be robot constants dot floor height. Now we could just type in a 0 here and it would do the same thing. But like I said before, we like to have our constants stored in just one place. That way, if we ever want to change something during competition, we just know it's going to be in the constants file. And then Now this is basically going to calculate like how fast to go, how fast the motor should go. So what we can do is actually just say this .io.set elevator, and the speed we want to go is going to be the speed that the PID calculates. So instead of setting the motor to be wherever the right stick is, we're setting the motor to be however fast the PID calculates it needs to go. So the PID is going to take in our current position and where we want to go, and it's going to use the constants here, and it's going to calculate how fast the motor should go to get us to where we want to go. So this is where we would then have to tune this by, increasing P, then increasing D, and some I, to get it so it can actually slowly lift up and get to the right spot. But we can't tune that until we have a real robot. So for now, we're just going to write the code, and then later is when you would actually connect to a robot and start tuning stuff. So now we have it so that the elevator can, based on what state it's in, start going to that position. Now all we have to do is basically make it so that there's buttons that's going to switch it to being those states. So similar how we have the intake where depending on what button you press, the intake goes into a certain state. We would want it so that depending on what button you press, the elevator goes to a certain state. Now I believe we've used up a lot of our buttons, like the green and red and blue buttons, which is usually what we would do for an elevator. So what we can do actually is just change these to be, let's say, the right bumper and the left bumper for intaking and outtaking. And then we made it so we don't actually need to press a button to turn the intake off. We just, when we're not pressing anything, it shuts off. So we can actually just get rid of that button now. And now all we have to do is just add the buttons for the 3 elevator positions. So we'll call it get elevator floor. And then usually what we do is, since the green button's on the bottom, we do that as our floor position. And then the switch is in the middle. So that'll be our red one. Then we have the scale. Then now all we have to do is go to Teleop controller. And right now we're basically just setting it. It's just in manual control all the time. So what we can do is basically, if you press one of the presets, it's going to switch to the state for that preset. So if we press the floor button, we're setting it to be in the floor state, and then we just kind of do the same thing where we just check all the different buttons, and then depending on what button, we go to the corresponding state. So now the only thing now is if we press these buttons, we're going to be switching to that state, and there's no way to get back to manual control. So we would probably add some kind of button that would switch the elevator back to manual control, just in case the encoder goes wrong. We've had that happen to us during competition before, and we needed to switch to manual control in the middle of the match. So that's always something that's good to have. But for right now, I won't add it because it would just be a separate button. Yeah, so now basically we have the dry base. We have an elevator that can use PID to get to different positions. The only thing we'd have to do is basically tune these PID values. But everything else is going to work. And the intake is just in and out. So now that we have that finished, basically all we need to do now is start working on autonomous control. So for this game, let's see here. For autonomous, basically all you what you had to do was drive across a certain line, which would help you get a ranking point. And then you could either place the yellow cubes into the switch or to the scale. Now this game had something that no game has ever had, where basically at the start of the match, the field gets randomized, which side is red and which side is blue. There were specific things that they would tell you in the code, and it would basically just tell you which side is red and which side is blue. And then we would have to have something in our code that was basically checking, okay, if the one right in front of us is red, put the cubes on the red one. Otherwise, drive over here and put them on the other side. Now, no other game has had that, so we're not going to worry about that. We're just going to pretend that we just only need to drive forward and place a cube into here. So you can see we're driving to a certain position. We're lifting up the elevator. We're lowering the elevator, picking up another cube, lifting up, spitting it out, going back down. So it's all just like repeated commands. And now since we added that PID control and those states to the elevator for our teleop, we can just use those same states for the auto. The only thing we're going to have to add is some way to have the drive to a certain position. So just like what we did for the elevator, where we added an encoder, we're going to do the same thing for the drive. Now the drive base, you want to have one encoder on each side. That way, when you're just turning in place, they'll cancel out and it won't think that you're moving. So we're going to make a drive left encoder. And then we're just going to set its ports here. And we have to make sure these are different ports to the ones we're already using. And then it's basically going to be the same thing where we're getting the encoder's position. Except this time what we're going to do is we don't actually care about the left and the right. We just want the average of them. So we're just going to say drive encoder. And then instead of just returning the encoder, we're going to return the average of them. So we're just going to add them and divide by 2. Oh yeah, so we need to do .get. There we go. So yeah, basically, because when you're turning, one half is going to go positive and one half is going to go negative. So if you add them together, that's going to be 0, which is what we want when we're spinning. We don't want it to think that we're moving forward or something. So now basically we have an encoder that can keep track of where the drive is. We'll make something that can reset the encoders. So now we can reset the encoders. because basically in our auto, we might want to, drive, turn, and then drive again. So we're going to want some way to reset them back to 0. Yep, so now we have the encoder. Now we can just kind of go into the drive. Just like how we did with the elevator, we're going to make a PID. And this is just going to control our forward and backwards movement. We could also do another PID for turning, either using the encoders, which isn't really recommended, or using a gyro, which just measures our angle. But the same thing is going to apply. So I'm going to call it our drive forward PID. That way, if we make a turning PID, we'll know which one is which. And then we'll do the same thing where we're going to have our PI and D values here. Now this would be something that we would want to tune, but for now we're just going to leave it at like that. So what we can do here is just basically make a function that's going to drive us a certain distance. Or what we could do instead is do that inside the auto command, which I think might be a bit easier actually. So basically now that we have the encoder, what we can do is just make an auto command that drives. So right now we have this blank auto command for just having the drive just wait. So we're going to copy that. We're going to rename it drive, just call it drive forward. And its a robot component is a drive. So depending on what subsystems we're going to want to use, we're going to need a component for each one. So we can just go ahead and add the elevator and the intake. Yeah, so now we have the drive command. We're going to put the first cycle at the top just so it's a bit easier to understand what's going on. So basically what we want to do is take in a distance that we want to go. And we're going to want to do a PID to drive forward that distance. So we just need to record down what distance we want to go. And then we're also going to make a PID. Once again, we're going to need to tune those, but for now, we'll just leave them all as zeros. So what we're going to do is during the first cycle, we're going to set our target. Now, since our encoders are keeping track of where we are, and we want this command to be like drive 5 feet forward from where we are right now, what we can do is basically just make our target be where we are right now plus where we want to go, or like how much we want to go. So we can make like a variable called target, and then our target is going to be where we are plus how far we want to go. Now we don't have IO. Oh yeah, we don't have an IO. I'm trying to get an encoder, but we don't have an IO here, so we're gonna have to add that. And we just forgot these brackets. So now since we have this IO and we're getting an instance of it, we can use the stuff from it. So now we can actually get the encoder values from IO. We're going to add the distance that we told it we want to go. That's going to be our target. Now all we have to do is every loop set our drive to be whatever the PID tells it to be. And then once we're within a certain range, that's when we're going to say that the PID is done and the auto command is done. So what we can do is basically just say, we're going to tell the drive how fast to go. So we're not going to turn, so we're going to set that to 0. And then how fast we want to go in the forwards direction, that's going to be the PID's output. So we're going to tell it where we currently are. And then where we want to go is going to be our target that we set before. Now, the only thing is this command is always returning true, which means it's going to finish right away. What we want to do is we want it to check basically if it's within a certain range, and then it will finish the command. So what we can do is just check if our where we want to be minus where we are is below a certain value. And if that's true, then we will finish. If not, then we'll keep going. So we can just say if is less than, now this is an encoder ticks right now, so we probably want a high number, but eventually we could convert this into feet or inches or something. Now the problem with this is this wouldn't let us go backwards. So what we want to do is actually get the absolute value. So it's always going to be a positive number. And then that way, the less than 100 is always going to work. So basically, if where we are, our target minus where we are is less than 100, that means we're pretty close to where we want to be. We're within plus or minus 100 of our target, so we should return true. And we can turn the drive base off. That way we don't accidentally coast and go too far. And if we are not within range, then we'll just return false. Now, the only thing is we're telling IO to set the drive, but nothing is actually calculating. Nothing's actually like running the calculate, which is what tells the motors what to do. If we go back into drive, just setting the drive only sets these variables. We need to run calculate, so it actually tells the motors what to do in IO. So what we can do is just add calculate inside of here. Oh yeah, so we're going to need to create an instance of drive. Oh, wait a minute. I'm sorry. This is the IO set drive. So this actually will just go straight to the setting the motors. So this will work. If we were telling this subsystem what to do, then we would also need to run calculate. But this auto command is just kind of directly telling the motors what to do, which is fine. We could also put this inside of here. So basically, if we're not in range, we'll just run the PID. Otherwise, we'll turn it off. Now, what we could do is if our PID can't exactly get within 100, we don't want our auto to just be sitting there. So what we can do is add a timeout value. And all of our auto commands have a built-in way to basically have a timeout value. So this is just the number of milliseconds we'll run the command for. And if we haven't finished, it will just automatically finish. And that's what we'll call this override function. So when we call override, we want to turn off the drive base. So we're going to do that. So now we have a function that will drive a certain distance forward in auto. We can go ahead and start making an auto now. So we just have this default mode that just does nothing. So we can just copy that and make a drive forward auto. So a lot of games have a points for driving past a certain line or into a certain zone. This game had one. You could get a ranking point for being in the right zone, crossing the auto line. So this is definitely an auto that we would actually make for this year. So we're going to go ahead and add a new command, which can be our new drive forward command that we just made. And we can see here it wants a distance and then it wants a timeout for like how long to run. So we can just say go 2000 encoder ticks. We don't actually know if that's going to be right. We can say you can take up to 4 seconds to get there. Go ahead and oh, I think there's a problem because we maybe named these the same thing and it's like not liking that. So we're going to call it drive auto line. Yes. Yeah, so it thought that this was the other drive forward. That's why you don't want to have things that are sharing the exact same name, because sometimes it doesn't know which one you're trying to do. And we need this drive wait here so that the auto doesn't end right away. So it'll wait until this drive command is over, and then it will end the auto. So yeah, now what we have to do is just add this auto to our auto selection list. So we go to auto control. Right here, we have our default mode. We can just add our new auto line auto that we just made. Now that'll show up on the list. And all of our like what auto we're selecting, we print that out. So you can just on the driver station see which auto you selected. Using the green and red button, I believe, on the driver controller. Auto mode increase is the red button. Auto mode decrease is the green button. Yep. So now we've made an auto that can drive forward, but we don't have any commands that can run the elevator or the intake. So if we wanted to do something more complicated, we're going to need to add those. So now in the auto folder, we have this drive folder. We're going to want to make one for all of our intake commands and our elevator commands. So we can just make a new folder here called intake. And we can basically just copy our basic drive wait command, turn it into an intake wait. Now it thinks it's from the other folder, so we just have to say that it's in the intake folder now. And the component, this is basically what type of command this is going to be. Instead of a drive command, it's going to be an intake command. And those components are right here. So basically you need to add them here if you're going to make more subsystems. So now we have intake wait. Now we probably want a command that where we can set the intake to be either intaking, outtaking, or off. Since our subsystem already has different states, we can do this in basically like two lines. All we have to do is make a new command, intake set state. And what this is going to do is basically turn the intake to a certain state, whatever you want, and just run calculate, and it'll never finish. So all we have to do is in the first cycle, well, first what we'll do is we'll take in what state we're going to set it to be. So basically we're going to make it private, intake state. I'm going to say current intake state. And then right here, we're going to take in an intake state that we want to be going to. Let's spell this right. Current intake state equals intake state. Then all we have to do is in first cycle, just say, tell the intake to be that state. So we need to get access to the intake. Get an instance of that. And now all we have to do is in first cycle, go this dot intake dot set state. And then we'll go this dot current intake state. So basically whatever you type in when you're making the auto, whatever you type in the bracket, that's going to be whatever state we're going to be setting the intake to. And all we have to do is in calculate, which is going to run over and over again. Just do this dot intake dot calculate. And then since we want this to go on forever and ever and never finish, we're going to make it return false. So basically, if we add this command somewhere, it's going to tell the intake to do something, and the intake will just keep doing that forever until we override it. So now if we wanted to change our auto, instead of just driving forward and then stopping, what we could do is after we're done driving forward and we've waited for the drive with the drive wait, we could turn on the intake. Maybe we want to spit out the cube that we start with. So we can just add a new command, our intake set state command. And then this is just asking like what intake state do we want to be setting it to. So we can do intake state dot outtaking because we want to spit out the cube. Now we're going to want to do this probably for a certain amount of time, maybe for 1 second. So we have in this util folder a couple auto commands that we have every year, so they always get copied over. We have one called auton wait, which basically just waits a certain amount of time in the auto. So we can wait for 1 second. Then all you want to do now is add command. Now all we have to do is basically have it so after the 1 second, the intake turns back off again. So we're going to override the intake basically to cancel this command because this command will run forever. Once we cancel it, now we have to run a new intake command, which is going to be the same command, except instead of telling it to be outtaking, we're going to tell it to be off. So now we have an auto that will drive 2000 encoder ticks, wait until it stopped moving, or until 4 seconds have passed if it can't get to the right spot. Then it will start spitting out the cube for 1 second, and then it will turn the intake off. Now the problem is we can't just drive forward and then spit out the cube. We actually need to lift up first and then spit out the cube. So what we need to do is make a new command for the elevator. Now we already have the elevator set up so it can go to certain heights. So all we need to do is basically make an auto command that's going to set the elevator to a certain state, just like how we have with the intake. And then we can start adding elevator commands to our autos just like that. I think I did that inside of this folder, which I don't want to do. There we go. So make an elevator folder. This is where all elevator commands will go. Copy the drive weight, rename it to elevator weight. Now you could have a command where you basically want the elevator to lift up to a certain position and also be at the right position. You don't want to spit out the cube while the elevator's in the process of lifting up. You want to wait until the elevator is finished lifting up and then spit out the cube. So we're going to have to add some more stuff to do that. This is a elevator command. So we're going to make a new thing called elevator. We could just call it lift. And this command is going to take in what preset we want to go to, what height we want to lift up to. So we're going to say what state we want it to be in. So just like how we have the intake set state, we're going to do the same thing. Except this time, this one isn't going to run forever. This one is going to stop once it gets to the right spot. And then other commands can run after this, such as spitting out the cube. So we're going to do a similar thing where we get the state and then set it. So this is basically what our desired state is going to be. We can add this dot. We don't have to, but it's just nice to add it. And then in our first cycle, we're going to need to tell the elevator to go into this new state. So we're going to need to access the elevator. So we're going to need to get an instance of it. So kind of once you get the hang of this, you can just kind of keep on making new commands based on what you need. So now we have access to the elevator. What we're going to do is say set state to be this dot elevator state. So just like with the intake where we set what state we want it to be, we're doing the same thing with the elevator, except instead of returning false, we want to sometimes return true when we're at the right position. Now, we don't have anything that's checking that we're at the right position. We just have it calculating and just trying to go to a position over and over again. We don't have anything that's checking if we're at the right position. So what we could do is we could have a function that basically just returns true if we're at the right position. We could say is at position. And then basically, depending on what state we're in and where we are, we can check if we're at the right position. So we can just kind of copy this over. Now, if we're in output control, like we kind of shouldn't be in output control when we're in auto anyway. So we can just say like false, return false. Now, when we're on the floor preset, basically what we can do is just check if where we are minus the floor height is within a certain range. So we can just say return, and then we can do the floor height minus where we are is less than a certain value. We have to do the same thing that we did with the drive, where we make it absolute, just in case we're coming from the other direction. I think I have one too many brackets somewhere. There we go. So basically, if where we want to go minus where we are is less than a certain value, that means we're at the right position. And this would return true or false, depending on if we're at the right spot. Now we just do the same thing, except instead of checking the floor height, we're going to check the switch height. Same here. We just need to return. Oh, I see. Yeah, this should just be if statements, I guess. Instead. Yeah, so we'll just do it with if statements instead. So we'll say if this dot current so if our current state is the floor state, then we'll return this. Else if we are in the switch state, we'll check if we're near the switch height. If we're in the scale, now we'll check if we're within the scale preset. Then we just need an else. So if we're in manual mode, this is what would happen. We'll just say we're not in range. So basically now we have a function that no matter what elevator state we're in, it's always going to check if we're within a certain range, and it will return true if we're within range. So now that we added that to the elevator, what we need to do is just use that in our auto command and basically say, do PID until you get to that range. And once you're within that range, then the command can finish. So what we'll do is we'll just say this dot elevator dot calculate, and then we can do if this dot elevator dot is at position, return true. But instead of doing an if and then an else, what we can do is just return if the elevator's at position or not. So basically this will be true and false based on if we're actually at the right position. So yeah, this command is going to tell the elevator what state we want it to be in. And then if it's in position at that state, it's going to finish this command. So basically it will lift up until we get to the right place we want to be at, and then it will stop the command, which is exactly what we want. We could do the same thing where we add a timeout. So if something's wrong with the elevator and it can't lift to exactly the right position, after a certain amount of time, it will finish no matter what. But we already did that with the intake, so we know how to do that. Now all we have to do is just add back to our auto. So we're going to drive forward, but instead of spitting out the cube right away, we want to lift up first. Now what we could do is drive forward, finish driving forward, and then lift up, or we could lift up and drive forward at the same time. To do two commands at once, basically, as long as you have them both running before a wait, they're both going to run at the same time. So we can just go new command, elevator lift. We want it to lift to the, let's say the switch height. So we're going to put it into the switch state. And basically now we're going to drive forward and lift at the same time. Now we're going to spit out the cube once the drive is finished, but we're not checking if the elevator is finished or not. So what we want to do is add a elevator weight as well. So now basically both the elevator and the switch, and the drive need to be finished before we go on to this code, which is spitting out the cube. And what we could do too is once we're done spitting out the cube and we turn the intake off, we could also lower our elevator back down to the floor. Just so it's not sitting there. So we could go here and we could say elevator state is now floor. And then we're going to wait until the elevator is done going down back to the floor. So now we have an auto that will drive forward, lift up, and then spit out the cube. So that pretty much covers, adding in subsystems and adding in states for them, adding in PID control, and adding in auto commands and making an auto. Does anyone have any questions about this? Because I know I went over a lot of stuff. Everyone's still here, right? Okay. Yeah, so this is this blank code that I started with before I started adding the elevator and the intake. We're gonna make that available on our Symbotics GitHub. Yeah, github.com/Symbotics. We're gonna add basically a template. We're going to have a one template for tank drive robots, which is what this one was. I started with our tank drive template. We're also going to have our swerve drive template, which is basically just going to have our 2022 swerve code in it. I think if I just open this folder. Yeah, and then basically this will be the same thing where all the subsystems are removed except for the drive base. And basically once the game comes out, if you were doing a swerve drive, you could pretty much use our code, which actually has commands for driving to certain points and stuff like that, and driving to certain angles. So you can pretty much just start from here with the drive base running and start adding in your other subsystems, depending on what the game is. Yeah, the Rogers thing has been going on like all day. Today I do have to head out at 3 instead of 4, just so you are aware of that. Yeah, so the main difference for a swerve drive is we actually have this built-in utility folder for the swerve. And we were using Falcon motors, so that's why we have this Talon here. But you could also switch these to Neos. You just have to switch some of the commands around with the encoders and stuff like that. But for everything that the Talon can do, there's probably an equivalent command for a Neo. Yeah, so like we're gonna post this publicly that way. So next year, if we do a swerve drive, we can just already have the code to do the swerve drive. This code we wrote during the build season this year because we never did a swerve drive before. A lot of the commands are using the WPI lib swerve code. They have a lot of built-in stuff that kind of automatically calculates the odometry and the kinematics and stuff like that. So you can see here everything that starts with WPI.first is basically built-in stuff. So a lot of the swerve stuff, like keeping track of our position, they just have built-in stuff where you just tell it what your encoders are and what your gyro is, and it'll just automatically keep track of your position. So having all that stuff, being able to reuse it year to year is definitely pretty helpful. The only other thing, I'll go back to what we were working on. Is instead of having the PID values being hard coded, so right now we just have them being, you would just type in, okay, 0.1, download this code to your robot, and then try it. If it doesn't work, you try a different value. The problem is downloading code to the robot. It's going to take time every time you want to do it. So what we do is we put these PID values on the smart dashboard. That way we can just kind of type in. I believe there is a page they have. Now the smart dashboard eventually might get replaced, but it's basically when you open up the driver station, you can configure it to also open up the smart dashboard program, and you could have variables showing up either with graphs or dials or these text boxes, and these boxes are where you could type in your PID values to tune them. Yeah, so right here, if on the driver station, if you press this gear icon, you could select a smart dashboard, and then you could type in your team number, and then basically when you're connected to the robot, whatever you put on the smart dashboard will show up. So you could just do like, you could put basically anywhere you could just have smart dashboard dot put number, and this is what's going to put a value onto the dashboard and create one of these text boxes. So whatever you put inside the quotes here is going to be like the label. So since we have an elevator and a drive, we're going to specify it's like elevator, the elevator P. And now this value is basically going to be like the default. So we would just say 0 for now, but eventually whatever value, after we're done tuning, whatever value we find is best, that's the value that we would want to put here, so that when the dashboard opens up, it already has the right one. And then what you could do is basically, when the robot first turns on, it's going to put all your numbers to the dashboard. And then what you want to do is basically read the values back. So it'll create a text box with the just 0 when you're first starting. And you could just kind of click into the text box and type in whatever number you want. And that number will be then used in your PID. So instead of having to download code, all you do is enable the robot, try lifting to a certain position. If it doesn't, if it's not the right PID values, you can just type in a new one, hit enter, enable the robot again, and try again. Now, what we do here is every time first cycle happens, we're making a new PID controller with the new values. So as long as this happens whenever we disable and enable, then that would update. If not, what you could do is just for testing, like have this PID happen in the calculate function or something, so it is always updating what the value should be. I wouldn't recommend doing that though. We just want to make sure that first cycle happens. Yeah, so I believe if you have like, you could just add in teleop init. It runs teleop control.initialized. Why is it not going there? Well, we can just go there ourselves. There we go. It's going to run initialize, which basically just runs first cycle of teleop controller, and teleop controller is running first cycle of the elevator. So yeah, every time we enable the robot, it's going to call this function first cycle. So it's going to set it to be output mode, and it's going to load the new PID values. So all we would have to do now is, instead of having it hard coded, we would read the value from the smart dashboard. So we do get number. We need the exact same thing in quotes. And then this is basically, if it can't find whatever you type in, it's going to load a default number. So you just want that to be 0. Now, whatever is in these quotes here, when you're putting a number, has to be the exact same when you're getting the number. So if you spell something wrong, it's not going to read the value. Whatever's in the quotes needs to match exactly. So actually, I put a space here and I didn't put a space there, so that wouldn't have worked. Now, this is just for the P on the PID. Obviously, you would want one for I and for D. Now, what we do, instead of putting them using this put number manually, what we do is in our robot constants, this is where we actually create all of our PID constants. So we just kind of have a thing that can record PID values and put them onto the dashboard. So we would just say PID constants. Then we would just say elevator. And then whatever we put here as our P, I, and D values, this is what gets saved. And then all you do is go elevator PID dot there was a way to do this. Let me go and check what we used to do. Oh, okay. So in the dashboard. Oh, okay. We need to call dashboard. Gotcha. And then down here, we just say dashboard. Yeah. Get PID. And then down here is where we put the PID values. Okay. So we just need to have a dashboard. Then we just say put PID constants. And then we're going to put the elevator PID. So this is going to put all these constants on the dashboard. It basically just kind of saves us time from having to type like elevator P, elevator I, elevator D all the time. It'll just automatically, it just helps us put a lot of values onto the dashboard. But what we did where we just put them in the elevator itself at the top, that works too. It's just like a easier way. So yeah, if we now that we kind of went through making a robot from scratch, if we look back on our 2022 robot, we can kind of see what a full robot looks like. So just like before, we had all the subsystems. Now the intake for this robot ended up being a bit more complicated because we actually the intake was also our feeding mechanism to the shooter. We just we put the functionality into one subsystem. We could have had an intake and then a separate subsystem for feeding the shooter, but we decided like they're pretty much always going to be doing the same thing. So we just made them into one that controls all the motors. That's why we have all these extra states. If we kept it separate, the intake would just have intaking, outtaking, and off. and then also up and down because our intake could lift up and down. But in a more simple robot, like our 2018 robot, the intake would just have 3 different positions, 3 different states. And it's basically the same thing where you have a thing for setting the state, and then you just, depending on what state you're in, that's how you tell what the motors to do, plus the pistons. And then there was some extra stuff we did because we had light sensors that would detect if we had a ball or not. And basically, if we had one ball in the robot, the bottom of the indexer would shut off, or the top of the indexer would shut off. And then if we had 2 balls, then everything would shut off. But the shooter, this would be similar to the elevator in the robot we just made, where it really only has a few states, depending on which goal we're aiming for. So just like how the elevator had the floor, the switch, and the scale, this has off, fender, and then the launch pad would be like the 3 different distances that we're trying to shoot from. And then just like with the elevator, where depending on what state you're doing, you read what RPM you need to go to from robot constants. With the elevator, we did the same thing, except instead of reading RPM, we read a height to go to. So it's a lot of the same things, just kind of repurposed, depending on what type of robot it is. But a lot of the things are going to be the same. And yeah, and in terms of our structure, like it's the same thing with autos, where basically you have the autos with the commands. Setting the shooter RPM is like going to a certain height, driving to a certain point. The only thing that's more complicated is our actual commands themselves, like driving to a certain position. Since this was a swerve drive, it could move sideways as well, not just forward. So we had a little bit more advanced stuff going on, where we had this function inside of our drive subsystem that would basically take a point that you want to go to and basically make 2 PIDs to go there instead of just 1. But it's sort of the same thing where you're basically looking at how far away you are from where you want to be, and then calculating a PID, and then telling the motors that's how fast you want them to go based on what the PID tells you. There's just some extra stuff we have to handle, like because we have a minimum speed and a maximum speed. So we just have a couple of things that are checking, okay, are we below the minimum, or are we above the maximum? But that kind of stuff you don't need. You can just add it if you need to have it. So yeah, that's pretty much how we started creating the code for this robot. If we look at our GitHub from source tree, we can see the different changes that we made over time. So basically, right at the start of the season, we just had a blank robot.java using the timed robot. And then here you can see I copied over our 2020 code, which was public, and then removed all the stuff that was specific to that robot. So basically, all these auto commands weren't copied over, and teleop controller is blank, just like how what we started with when we started making the elevator robot. And then basically, the first subsystem we did was the intake subsystem, because we knew no matter what our robot is, we're going to have some way to pick up the balls. So we just started adding the states for that, and then pretty much just got the students working on doing stuff. And what's nice about having these different subsystems is you can say, okay, one student, you work on the drive while someone else works on the hanger, while someone else works on the intake, and they can all kind of work on them on their own. And then once they're finished, they can put it onto the GitHub and get it all merged together. Yeah, and it looks like here, right. So yeah, January 30th is when we started actually testing out the robot. And you can see we're just making changes to like how fast the intake goes. Oh no, January 30th. This must have been when we were just testing. We got every student to make one change to the code and to push it, just so we made sure they were all able to use source tree. That's what this is. Yeah. We didn't actually start testing the robot until probably around here. Yeah, because this is when we first added the swerve code, not until February. Yep. So yeah, just once again, we're going to put our template code onto our GitHub, and you guys can copy it and download it. And we'll have the tank drive version and the swerve drive version. And then basically you can just kind of follow along and do what we did, where we started making the new subsystems and adding the motors and all that. But yeah, that's basically, you know, how on 11.14 we program robots. Does anyone have any questions? Either about, you know, a specific thing or just a general, like, hey, I want to program this, like, what's the best way to do it, or anything like that. I can just answer questions for the next like 15 minutes or so, and then I have to head out.
Hi there, I have a quick question.
Yeah, sure.
So Ian McTavish, 4152. We have successfully used Pid Control with the elevators before, which is
Right.
great. The issue we had in deep space was Pid Control going down was an issue, because it would slow down and then all of a sudden it's slowing down and you've got gravity, and
Right.
that was an issue. So we ended up, like, once it passed a certain point, we just turned it off because we found we needed it to go down fast enough to actually go down. Any strategies with that?
Yeah. So yeah, I actually should have went into that. What you can do for an elevator with PID is you can, instead of telling the motors to be going to what the PID tells them to go, what you can do is just tell them to go what the PID tells them to go plus a certain constant. And basically this constant will be whatever amount of power the motor needs to counteract gravity. So that way it can hold itself at a certain position. And then what you can do too is when you're trying to go to the floor, and if you're finding that your PID is kind of either it's kind of jumping up and down when it's supposed to just be resting on the floor, what you can do is you can PID down to the floor, and then once you get close enough, you can just shut off the motor. That's what we did.
Okay, yeah.
Yeah.
So thank you.
Yeah, I believe in our 2019 code here, for some reason we called it lift instead of elevator. Yeah, so right here we say if our lift state is trying to go to the ground and our height is less than this, then just turn it off. So basically, if we're already close enough to the floor, to shut off, and then after that, we would do the PID instead.
Thank you very much.
Yep, no problem. Has they used the Romy? No, I've heard about it and read about the Romy, but we've never gotten our hands on one. Seems like teams have been using them on Chief Delphi. I've read teams using them. right, so doesn't seem like anyone has any questions, and I ended up finishing a bit early here. I'm still the host of this. Finish the session about Romy.
Good afternoon. Thank you again to Caleb. I'm barely hanging on with hearing it so loud out here at Tim Hortons. And I was following along as much as possible. It looked great. Looking forward to seeing the recorded session. And we'll hope to see everyone very soon. If there are any questions, please feel free to email, and we will be glad to set up more mentor sessions or assistant support in whatever way needed. And so that was really great. Thank you very much again, Caleb.
No problem. And I think we might make a public post or something when we do finally post those templates for everyone to use. So just stay tuned for that.
Okay, well, thank you very much again, and we'll see everyone very soon.